All right, so for announcements today, we've last, I think, 4 lectures been covering economic order quantity model, when demand is known, when demand is constant, and when it's continuous. And I have 2 assignments that are up about that. I'll kind of give you a preview of them real quick. Both of them are in the module that says Lecture Set D, Inventory Management. And so you see Assignment 1 and Assignment 2. Assignment 1, that's the one where you can go ahead and get a hard copy of it in advance and know exactly what it is. It's going to require you to go to a spreadsheet and get your particular values for R, H, C, D, and L like we did in last class. Yeah. Yeah, it's almost identical to it. So if you, like the hard copy is saying, okay, go get your values for question A. So this is A.1, and it says A.1 means use the values of R, H, and D, and C for question A in the spreadsheet. So there'll be a row with your name, and it says question A. Use the values of R, H, and D on it. And it's going to ask you, what's the optimal value of Q? And you're just going to put an answer there. And notice that you don't have to show your work or anything. And notice that it says, just like we did last time, I want you to perform all the calculations in Excel where you don't have to worry about rounding. But when you report your answers, round to 4 decimal places. And it says it here. So for question A, you're first going to say, what is Q star? Then you're going to tell me what T star is in fractions of a year. Then you're going to tell me what T star is in days. Then you're going to tell me optimal number of orders to place each year in star. And then you tell me the reorder point for inventory on hand, the point at which inventory position reaches a certain level that triggers a new order. And that will complete, say, question A, and then question 6 is identical. The only difference is that you've got different values of R, H, D, and C. So that's one that you can, let's see, these aren't due till midnight, March 23rd. So you can print that thing off, do all the calculations. You can set up a Excel spreadsheet to do all the calculations and just plug different numbers in for question A, question B, and then just put your answers there. This is one I obviously hand grade, so I have to go in there, look at your answers, because not everybody has the same answers. Any questions about that? So I personally think that that's very easy. It's worth 300 points. And then assignment 2 is harder. I believe it's worth 400 points. I don't think assignment 2 is hard if you know the model well, meaning if you go back to, I even say in the announcements, the best way to study for it is to revisit the entire lecture on March 2nd, the last lecture we did. And this is an assignment 2. There's no time limit to it, so you can work on it at different points in time, which also means you can like print off the test, save your answers, check back later, things like that. It's due the same time, March 23rd on midnight. People will have, there's a big question bank, and when you pull it up, it's going to generate 20 questions from that question bank for you. So people will have different questions. And to give you an idea, I'll do a preview and it'll generate some of these questions. And so some are like this: as lead time rises, what happens to the inventory position, the value of inventory on hand, at which point a new order is placed? That's like what we were going over last time. As R rises, what happens to T star? This is a question making sure you understand what cost factors are included in that total cost formula. There's questions like this where you have to do algebra with exponents, so it's going to give you a question like that and you say whether it's true or false. There's some Here it's going to say if T equals 0.12, what is N? So that's just a quick calculation. Maybe some questions about the model. So an EOQ model with lead time and continuous and constant demand. Every day the firm uses the same amount of inventory, true or false. Some derivative questions, simple derivatives, some matching. What is R, H, D, and C? Is this the derivative of that? Suppose D is this, H is this, and Q star is this. What's the annual holding cost? And so on. And again, the information on this is put in the announcements for today. Assignment 1, about assignment 2, how to study for it. Do remember that the bonus master production schedule assignment is due March 15th at midnight. Any questions? Okay. There's two things we're going to be working on today. Every now and then I'm going to be putting a handout up. Economic order quantity with stochastic demand. That's the one I handed out earlier, also available in Chapter 9. I just handed out some worksheets that say at the top, worksheet given on March 9th today. The questions on there are also at the end of March 2nd worksheet that we never got to. And there was an exam 2 from 2019 that I gave out like 2 weeks ago, and we're going to be going back and doing a question from there. And I think you can do most of your work on the worksheets today. Other stuff I'm doing is already in some handouts. So we had the old EOQ model, the one we've been working on the past 2 weeks. That's the economic order quantity model, where we're mainly focusing on how much to order and when to order. Where if we graphed demand over time, it looked like this. Where demand could be, like if we're stocking things on shelves, it's like demand each day that we expect consumers to buy. Or if we're thinking about chicle base for our natural chewing gum factory, we're thinking about how many pounds of chicle that we need. And in that model, we needed the same amount every day, one day to the next. We needed the same amount in any 1 hour on one day as we needed in any 1 hour on another time. And it was completely fixed. It was just a number, and it was known. And that made things a lot easier. But now we've got the economic order quantity with stochastic demand. And stochastic just means random. Our main demand variable is going to be little d for daily demand. So rather than concentrating on big D, the amount we need all year round, we're concentrating on little d, what we need on any one day. And in this case, demand there's a pattern to demand, but there's a lot of randomness to it. We don't know exactly what daily demand will be. They can have big ups, we can have big downs. There can be some times when it's pretty stable. But even though it's random, it's stochastic, there is a pattern to it that we can exploit to help manage inventories. Like if this was a historical pattern of daily demand, we know that the mean is about right here. We have an idea of how much higher demand can be on any one day relative to average, and we're going to be focusing on those patterns. And so it's kind of like, if you go up and you're playing softball, when you hit a softball, almost every hit will go a different distance. But there's some pattern to your distances. There's some your average hitting distance, and there's some variance or standard deviation to the patterns of your hitting distance. And so if I wanted to try to figure out how far Stevie Ray's gonna hit, and if I have data on his past hitting patterns, I know on average how far he tends to hit. I know how far it can sometimes go when it's a really good hit. I know how embarrassingly short it can be when it's a bad hit. And so I can use that pattern to say where I should put Stevie Ray Vaughan in a softball lineup. That's the same thing what we're doing here. It's the same general problem. We're trying to figure out when we should reorder. The amount we reorder is going to be exactly the same. We're going to use the same formula, but now we're mostly concerned about when we reorder. And the description of this model, this is the figure from the textbook. And when you first look at that model, it looks like it's more complicated than the model we did with, but fundamentally it's actually a bit simpler. And to show you this, let me start you off with a simple thought experiment. And we're now going to the worksheet for March 9th and question 1. Okay. And for our online friends, obviously you can't read this, but on Canvas you can print out this worksheet, and so you can read it along with us. Here we're just going to do just a common sense estimation of how we should manage our inventories. We say we have a coffee shop. And in this coffee shop, we know that the lead time is 7 days. And so from the time we place a new order for coffee until the time it arrives, there's a 7-day period. And what we want to do is we want to say, okay, I want to figure out how low my coffee inventories need to get before I place a new order. And when I place a new order, I know it's going to be 7 days before it gets here. And there's a trade-off there. Holding inventories is costly. For one thing, you want as fresh coffee as possible. So I want to figure out how low my coffee inventories will get before I place a new order, such that after 7 days, when the new coffee arrives, I've never run out of coffee, or at least the chance of running out of coffee was really, really low. And when the new order arrives, I have very little of my old coffee left. That's what we're looking at. And the demand or the need for coffee on any one day can differ from the next. But we've been running this coffee shop a while. We have some historical data to look at. Even if it was a new shop, we could make some pretty reasonable guesses about what demand might be. And I have here, it says on an average day you use 50 pounds of coffee. And so one thing you could do is you could say, okay, lead time is 7 days. And on average, I use 50 pounds a day, so maybe I want to reorder when my coffee supplies are only 350. We only have 350 pounds left. But that wouldn't be wise, because that 50 pounds was an average, meaning half the time people are ordering more than that. So if we did that rule, there's a very good chance we would run out of coffee before new customers, before the new shipment arrives. Well, we say, okay, let's forget about the average. Let's say, like, what's a busy day when people are ordering a lot of coffee? And on a busy day, you may use up to 75 pounds. And we say, okay, worst case scenario, after we place an order and we're waiting for the new coffee to come in, we have a busy day every day for 7 days in a row. In that worst case scenario, I want to make sure we still had enough coffee on hand to be able to sell everybody who wanted a cup of coffee or a cup of coffee. And so we can just make the simple calculation where we say reorder when coffee inventories equal lead time is 7 days, and on a busy day, if we had a busy day every day for 7 days, we'd be using 75 pounds of coffee, £525. That's a very reasonable idea of, if you do that rule, say, well, whenever our coffee inventory reaches about 525, let's reorder. And even in a worst case scenario, you're probably not going to sell out. And in that worst case scenario, you may be almost run out when the new coffee arrives, but you haven't completely run out, the new coffee's there, you replenish it, and so on. Okay, that's really simple, right? That's really all we're doing with the economic order quantity model with stochastic demand. We're just going to make it a little more fancy, because here we said 75 was the biggest day. Let's just make sure we don't run out if we have 7 days in a row of our really big days. We can add probability statements to this, and that's what we're going to be doing. But essentially, this is the rule we're trying to come up with. We're saying, how low do supplies need to get before we reorder? And of course, in the real world, you could just you do a rough calculation like that, 525, and you say, okay, let's just make it 550 and be extra sure. That makes sense. But of course, sometimes if you're programming things in a computer, you may want it to be a little different. If you're managing a lot of things at once, you may need some automated rules, and so you may want to make it a bit more mathematical. So now we're going to number 2. And this is the model we're going to be working with. So now we're saying that demand is stochastic. And like before, giving you little c, little r, little h, lead time. I always have to give you those things, because with the coffee, we just said when we reorder, but when we decide how much to reorder, we're going to use that same q star equals the square root of 2rd divided by h, and we'll do that calculation in a minute. And so we have all these, we have the 5 days. Usually I would give you a D equals something, but now it's stochastic. I can't tell you one number. I have to tell you it's stochastic, and I'm always going to give you a mean and a standard deviation. And what I'm going to do, when you do an assignment on this, you're going to be given data. And each of you is going to be given a different data set. And there'll be a couple hundred observations, and what you'll have is daily demand, little d. Daily demand for a large number of days. And so like that 5099 is little d for March the 2nd, 2019. And as you see down there, number 3 and number 4, you need to calculate average daily chicle use and standard deviation of chicle use. And you can just do that in Excel. I'm just going to briefly remind you what a variance and standard deviation is. I know you had statistics before, but I also know what senioritis does to the to your thinking bone. Okay. Okay, I don't think you need to write this down, just look along with me to get it. You have little di, which is demand on day I. You know, I can be 1 for March 1st, 2 for March 2nd, 3 for March 3rd, and so on. And then mean, which we usually always denote by mu, is just always you take the sum of all the di's. So if di's went from 1 to n, maybe like n is 300 for 300 days of daily demand, you sum up all the daily demands and you divide by the number of observations, and of course that's going to be your mean. Just your average, same thing you know how to calculate. But then what's particularly important is because demand is stochastic here, sometimes it can be higher than the average, sometimes it can be lower than the average, and we need to know that pattern. So if we're thinking about Stevie Ray Vaughan hitting a softball, you know, maybe his average hit is, let's say, 100 feet, and maybe it tends to be 95% of the time it's between 25 feet and 175 feet. We want some kind of idea of what that pattern can be, and to do that we always pair the mean with the variance or standard deviation. And so we have the variance, which we denote as sigma squared, and like you can see in number 2 we have sigma squared down there. And what sigma squared really is, we're first taken, maybe we have 300 hits on Stevie Ray Vaughan, and we have his mean. So we take each hit, 175 feet, another's 130 feet. For each hit we subtract the mean, so one time is 25 feet above the mean, another time is 33 feet below the mean, and we square it. So we get an idea of the squared deviation from the mean. And it's like we've taken an average of the squared deviation from the mean. But for reasons you're not prepared to understand, you don't divide by n, you divide by n minus 1. I think I was in my PhD program before I ever saw the derivation of why that was so. And so the variance is just like the average deviation, average squared deviation from the mean. It gives you an idea of, you know, if you're thinking of a bullseye, how, when you're shooting at it, how the deviations around the bullseye. And then what we often use is the standard deviation, which is just the square root of the variance, which is just sigma. And what you might remember from your statistics class, we really like the standard deviation because we know a lot of things in the world behave like a bell-shaped curve, and when things behave like a bell-shaped curve, that standard deviation tells you a lot about its behavior. If you didn't understand that, if you don't really recall it, that's perfectly fine. You can figure it out on your own if you want, but that's just a recollection. What you need to do for this class is know how to use the mean and the standard deviation, and how we use it is actually pretty simple. In number 2, it says demand is distributed I, D, normally, You may or may not have seen that kind of notation before. It's fine if you have it, because I want to tell you what it is now. So we're going to be answering number 2, what does it mean? The IID. Identically, independently, distributed. So IID means identically, independently distributed. So this means that we have some kind of idea of the pattern of daily demand. And identically means that pattern is the same from one day to the next. So that mean and standard deviation is just as good for describing daily demand, daily needs for chicken base on one day as the next. The independently means that needs for chicken base on one day are completely independent of needs for chicken base on another day. And that's an assumption that we're using here that sometimes is not a good assumption, and we'll see later how we can get around that. So what this means is that, like, if Monday we need a lot more chicken base than we normally do, then that doesn't say anything about what we need as far as chicken base the next day. Whereas in reality, that probably isn't about right. You know, imagine you're a restaurant, and if you have a really busy day on one day, that may tell you something about what business is going to be like on the next day. So, for instance, you're an ice cream shop, and you have a really busy day today because it's really warm weather and people are out. Well, there's a higher probability that it's also going to be a warm weather tomorrow, and so you're most likely going to have a higher than average number of customers tomorrow. So that's a case where daily demand between 2 days is positively correlated. One tells you something about the behavior of the other. They're not independent, where we are assuming independent here. On some other times, like if you might think about, let's say, milk needs at Walmart. If one day you have a lot of milk sales, it may just be that just randomly a lot of people went to Walmart at one time to buy their weekly milk needs. Well, if a lot of people came today, then those people aren't going to have as many milk needs the next day. So high sales today may mean lower sales tomorrow. That's a case where demand on one day and another day are negatively correlated. They move opposite directions, where again we're assuming independence here. A lot of times you can just assume independence even if it isn't true, because it's just close enough. It works well enough. But after we get this model, we are going to do a thing in Excel where we show how we can adjust the model to account for the fact that sales might be correlated over different days. Number 3 and 4 is asking what's the average daily chicken use and what's the standard deviation of daily chicken use. And sometimes in a question I may give that to you, sometimes I'll give you data where you have to answer it. And so in this question, I've given you some data on daily demand, and when you do your assignment for this, everybody's going to have their own data for daily demand. And what you can do is you can just use Excel to calculate it. So, you know, you don't need to know the formulas for standard deviations, because Excel can calculate it for you, and Excel will do it well. And so over these days, if we want to know the average, we just have say Excel give me the average daily sales. And it's given me this is the average. And then the standard deviation, you know, if you forget the formula, just Google it, you know. Standard deviation.
Is it .ev?
What's that?
Or which standard? I know that there's two in itself.
Yeah, there's the sample or population. You can just use the sample one because what we have is a sample, not a population. So we're using stdev.s. That's the one that's going to divide by n, not n minus 1. .862. And it can also give you the variance var.s for the sample variance. So that's the standard deviation. This is the variance. And of course, if you did it right, if you square the standard deviation, you should get the variance. And so our answer for number 3 there, what's average daily chicle use? We can say mu is 5192.5. If you're doing a test or something, I always tell you how many decimal places to use. Number 4, what's the standard deviation of daily chicle use? Our sigma there is 275.86. Now for answer number 5 and number 6, that's what's particularly important. Now I'm just going to show you something real quick about this. So our lead time here is 5 days, and number 5 says what's average chicle use over 5 days, what's standard deviation of chicle use over 5 days. And remember the coffee shop sample. The coffee shop example where we said, okay, suppose we have a certain lead time, and let's suppose lead time is 5 days. We need to reorder when we know we're not going to run out of coffee in those 5 days. And we're doing something similar to here. We're wanting to know what's the average amount we might sell over 5 days, what's the standard deviation of sales over 5 days. So we're going from the information we have on daily use, mean and standard deviation of daily chicle use, to the mean and standard deviation of chicle use over lead time, which here is 5 days. And so, mean demand over lead time is pretty simple. You just take your average daily use and you multiply it by lead time, multiply it by number of days. And our average daily use was 5192.5, so that's the amount average we use every day. And then lead time is 5 days. And so on average, over a 5-day period, we're going to need close to 26,000 pounds of chicle base. Of course, that's the average over 5 days. If our rule was to reorder whenever chicle base hits about 26,000, then about half the time we'd run out before the new chicle base came in. And so we want to also not just look at the mean, but look at the standard deviation of demand over lead time. So mean over lead time was easy because it's just U times L. The variance is similar. It's similar. The variance of daily demand is sigma squared, so variance of daily demand over lead time is just sigma squared times L. But of course, remember, the standard deviation is the square root of variance. And when we take the square root of that variance over lead time, that too is going to go away, but we're going to have a square root of L. And so our standard deviation over lead time is the square root of the variance over lead time which is sigma times the square root of L. It's just the way it is. There's a derivation behind that. It uses some horrible math with lots of integration and stuff, but that's how it works. And so now for answering number 6, our standard deviation of daily demand was 275.86. Lead time was 5 days, so times square root of L. And I should have had, instead of L there, 5. I'm just plugging in for what L is. And so over any, now we know what the average needs are, average demand over 5 days, and now we know the standard deviation around that mean over the 5-day period. And we finally use that for this. In one of the handouts, that's in the handout with this, the EOQ with stochastic demand, it's got some figures on the back. This is also a figure in the textbook. This is a reminder about the bell-shaped curve. And the bell-shaped curve is so useful because what we know is for any normal, oh, by the way, so there was the question, I skipped over this. On number 2, what does this mean? D, tilde, IID, N, mu, sigma squared. The N means normally distributed. So write that in. I forgot to put that. The N on number 2 means normally distributed. Bell-shaped curve, like what we have here. Okay, so what we've done is we calculated average demand over lead time. Our average demand was close to 26,000. And we calculated the standard deviation of demand over mean time, over lead time. So what we can do is we can look at a bell-shaped distribution and we can say, okay, if we're 2 standard deviations to the right of the mean and 2 standard deviations to the left of the mean, 95% of the time the value will be between those 2. So 95% of the time our demand, our needs for chicle base over a 5-day period are going to be within 2 standard deviations of the mean. What that also means is that 5% of the time it's either going to be lower than 2 standard deviations below the mean or higher than 2 standard deviations above the mean. And since this distribution is symmetric, this area plus this area must equal 5% to the same area. So this little area right here is going to be 2.5%. And now for the denouement. And we are about to answer, okay, yeah, we've answered number 22. About 95% of the time, daily demand will be between 2 standard deviations of the mean. 2.5% of the time, daily demand will be greater than 2 standard deviations above the mean. It's the same if the mean and standard deviation is for demand over lead time. So what this means is that thus, demand over lead time, which again means during lead time, during those 5 days when we're waiting for the new shipment to arrive. Demand over lead time will exceed this is the equation we're working to. S star is going to be our reorder point, and so mu times L is demand, average demand over lead time. Sigma times square root of L is the standard deviation of demand over lead time. So if we take that standard deviation, add 2 of them to the mean, so with 2 standard deviations above the mean, then our needs over that lead time will only see that value 2.5% of the time. So we've got this rule. We want to say, okay, how low do inventories need to get before we need to reorder? And in this class, when we're doing these problems, we're always going to say, so you know this is just how we're going to answer it, that we're always going to reorder when our inventory gets so low that there's only a 2.5% chance we'll run out before the new order comes in. That's the rule we're going to use. And so that means we want to reorder when our inventories of chicle base reach this point, 2 deviations above the mean, when we're talking about demand over lead time. When it hits that point, that's when we reorder. And when we do that, we know that 98.5% of the time we won't run out before the new order comes. So I know a lot of that was stuff you've seen before, but you don't remember. But what we're getting to is actually just a really, really simple rule. You know, calculating U times L is easy. Calculating 2 times sigma times square root of L is easy. And you just say reorder when you hit that point. When you hit that, the S means like stock there, stock level of that. That's all there is. That's when you reorder, how much you reorder. Even though this has the stochastic demand, that Q star rule is still a pretty good one to use. Square root of 2 RD divided by H. Let me make sure, okay. So we are answer number 25. So you're trying to figure out when a new order of chicle base and you want there to be only a 2.5% chance of running out while the chickle's in transport. At what point should inventory on hand reach before you place a new order? And so we're now going to plug in the numbers. That's our rule. And you've even got a handout that says that everything's always going to be open book. And we know that we already calculated that mu times L was 25,962. I'll just use no decimal places, plus 2 times sigma times square root of L was, let's just say, 617. And you see where I got those numbers, right? We just did that. So you're reordering when your inventories of chicle base get as low as about 27,000. And then how much should you reorder? That's number 25. So when you reorder, you're just going to use the same formula because it's a reasonably good formula. But the thing is, I haven't given you what big D is, right? We said D was stochastic. And so we need a good proxy for it, a good estimate for it. And so remember, big D is total needs over a whole year, 365.25 days. We just need a rough number for what that might be. And so it's reasonable to take the average daily demand and multiply it by 365.25. So we estimate big D, which I know might look as like an O, as about 1.8 million. Now we can go back to this formula and we can take square root of 2. We said R was 3951. We said big D was a really big number. And H was 5. $54,750. Okay. So tying this all together to reiterate, we order Q star equals 54,750 units when inventory equals S star, which we said was 27,196. So that's it. That's the end thing of what we're trying to do. We know how much to order and when we need to reorder it, and when we do that, only 2.5% of the time will run out while the new order's in transport. Assuming daily demand really is independently, identically distributed, normally, of course, you have to assume something. Okay. One quick question. So there'll be, this, I think, one more lecture on inventory management. So one more lecture, that's a class kind of like this. Then we're going to be going to transportation logistics and programming. That's where we don't do as much calculus. We don't do any calculus really, or math by hand. We are doing conceptual algebra, seeing what a model looks like. We're setting up a really big model in Excel, and we're having Excel do the number crunching for us. So like a big problem, like if we have these 25 factories who can supply this 3 distribution centers to to restock 500 different Walmarts, what should we take from each procurement center through which distribution center to go to which Walmart shops? A horribly complicated problem, but computers can do it really easily so long as we set it up nice. So it's mostly getting things organized in Excel. And so I need to know that different ways I can teach this. If it's a regular class where there's no online section and stuff, and everybody has a computer, I would have everybody bring their computers and we'd all be doing computer work at the same time. That may not be the best way of doing it. So let me do this. So raise your hand if you don't have a decent personal computer you could bring to class. If you don't have. I'm assuming if you have a PC, you have Excel on it. Raise your hand if you have accessed Google Drive before, like Google Slides, Google Docs, Google Sheets. Raise your hand high if you've done that. Okay. Okay, good. So let's see, I'm guessing after this week, you'll want to bring your computers with you to every class. I think that'll be the best way to learn. You know, if you forget of something, of course, we have an online section. I'll have videos of the screenshots and stuff that I can put up for you as well. Sound good? Okay, see you Thursday.